We move on to learn about gravitation. The force of gravitation is a fundamental force in nature, is a very important force. It is responsible for the equilibrium of the solar system, the galaxies. It is all governed by the gravitation force. In 1686, Isaac Newton knew that a net force is needed to keep moon rotating around Earth. He knew that if there was no such force, no centripetal force, then the moon will fly away, will not continue to move around Earth. And he knew more than that. He knew that the same gravitational attraction between moon and Earth, the same force of gravity, is responsible when you have an object at the Earth's surface. The same force that makes an apple fall from the tree downward, not upward, is the force of attraction. It is the same force that keeps moon falling toward Earth. But because it's in circular orbit, it will not actually descend down. It will just maintain the circular orbit. In general, any two objects with mass m1 and m2 separated by a distance r will have a mutual force of attraction that depends on the product of the masses and inversely on the square of the distance. So the force of gravitation between these two masses may be expressed as m1 m2 over r squared multiplied by a constant. This is just a proportionality constant, which depends on the units that we are using. If we are using SI units, mass in kilogram and R in meter, then G is 6.673 by 10 to the minus 11. That would be meter squared divided by kilogram second square. This should be meter square, not meter cube. When you have spherical objects, we can ignore the dimensions and think of the masses as if it is located at the centers. Because when you calculate the force, you need R. So we take R, the distance between the two centers of these spherical objects. The force of gravitation is needed to maintain the circular orbits. If you consider any object in an orbit, it will be attracted by some acceleration toward the center, like objects around Earth, like moon, or like objects at the surface of Earth. This force, mg, is the same as g, the product of the object mass by the mass of Earth divided by r squared. So you can cancel m with m, the object mass, and g, the gravitational acceleration, is simply the universal gravitational constant g multiplied by m divided by r squared. If you are talking about the Earth's surface, you need to substitute here the mass of Earth, and this is the radius of Earth. When you do that, substitute for g for mass of Earth, for radius of Earth, you will get for g 9.8 meter per second squared. That is the gravitational acceleration at the surface of Earth. As we go higher away from the center of Earth, g decreases. So at an altitude of 1,000 kilometers, it is 7.33. At an altitude of 5,000 kilometers, it is 3.08. At an altitude of 50,000 kilometers, it is 0.13 meter per second squared. So now we understand how g changes for space trips as the spacecraft moves away. The effect of g gets less and less. Example: An astronaut standing on the surface of Ceres, the largest asteroid, drops a rock from a height of 10 meters. It takes 8.06 to hit the ground. Calculate the acceleration of gravity on Ceres. Find the mass of Ceres given that the radius of Ceres is 510 kilometers. Calculate the gravitational acceleration 50 kilometers from the surface of Ceres. This is just an example to practice the new law that we learned about. So the distance here is 10 meters. It is inward, it's going down, so it's with a minus sign. Initial velocity is 0. The acceleration is the gravitational acceleration of Ceres. The time involved is 8.06 seconds. From the kinematics equation, delta x equals v naught t. V naught is 0, so that term is 0. We end up with just half at squared. So minus 10 equals minus half gc t squared. We have one unknown, gc, the gravitational acceleration for the asteroid. We solve for it. It is 0.308 meter per second squared. Then mgc equals g mass of Ceres, mass of the object divided by the radius squared. So from this equation, you cancel m with m, and so for mc equals gc rc squared divided by g. We substitute here for gc, we substitute for rc, the given value, we substitute for g, the given value, 6.67 by 10 to the minus 11. Evaluate, so this is the mass of this asteroid. Then calculate the gravitational acceleration 50 kilometers from the surface of Ceres. So in this case, we know what is r, and we calculate g prime, the gravitational acceleration at that distance, using a Newton's law of gravitation. So it is 0.255 meter second squared. It changed from 0.308 meter per second squared at the surface to this new value at 50 kilometers away from the surface of this asteroid. As we know, potential energy depends on the position. We learned before that an object of mass m at a height h from the surface of Earth will have a potential energy mgh. So now, with the new information about gravitational force, we can talk about a potential energy that can be calculated from this equation: minus g, mass of Earth, multiplied by mass of object, divided by r. R is the distance from the object to the center of Earth. Like all energies, this is measured in. If you are talking about the surface of Earth, then r would be the radius of Earth. But as the object moves away, the potential energy gets less and less because r increases as the object moves away. At infinity, when r is infinity, the potential energy goes up. And the opposite is true. As the object approaches Earth, r gets less and less, the denominator gets less and less, so the potential energy increases. Okay? If you consider spaceship or satellite at some height h from the Earth's surface, that would be the potential energy at that location. You just replace r by the radius of Earth plus h. Then when that spaceship is on Earth's surface, we are dealing with just the radius of Earth. So that would be the potential energy at that location, and this is the potential energy at this location, and this would be the change in potential energy. From the conservation energy, the change in potential energy is equal to the change in kinetic energy. As the object falls down, its kinetic energy will increase, its velocity will increase. So here we substitute for the two values of the potential energy and simplify, we will have this result. Okay, you can simplify it further. This is approximately equal to 1 over RE squared, because h, if you are near Earth, h can be neglected compared to the radius of Earth. Radius of Earth is 6.4 by 10 to the power 6 meter. We know that this quantity gme over RE squared, this is g. So the change in potential energy is equal to mgh. Now, in the case of space missions, the spaceship will be accelerating upward to escape from the gravity of Earth. Initially, it has some values for the kinetic energy and the potential energy that we can calculate from this formula. Then, when it escapes from the gravity of Earth and goes to outer space, far away from Earth, the final velocity will be 0 and the distance r is infinity, so both energies are 0. And now we can solve for the escape velocity, the original velocity that will allow us to reach this situation. So from this equation, the escape velocity equals 2g mass of Earth m for the spaceship divided by the radius of Earth. When we use this equation for various planets, for Earth, it is 11.2 kilometers per second. That is the minimum velocity for any spacecraft that needs to escape the gravitational force of Earth. It should have this escape velocity, 11.2 kilometers per second. So now we understand why we need to burn a huge amount of fuel in the early stage of any space mission, such that the spaceship will be able to escape the gravity of Earth to reach this high velocity, 11.2 kilometers per second. As you can see for other planets here, you have different values. For Moon, it is 2.3, because the gravity on Moon is much smaller. It's 1/6 the gravity on Earth. Okay. On the other hand, if you take Jupiter, which is the most massive planet, you are talking 60 kilometers per second. You can imagine if such a space mission went to Jupiter and it want to return back, it would be very difficult to do that, because you need to escape that gravity, that gravitational field. You need huge amount of fuel to escape the gravity of Jupiter. We move on to Kepler's laws. These are important laws when you study astronomy and astrophysics. The story goes back to the 16th century. A Danish astronomer, Tycho Brahe, did several measurements using the technology at that time, and was able, based on observations and calculations for 20 years, was able to put estimates for the solar system, various planets and their separation from the sun. Then his assistant, Johannes Kepler, used the data that Brahe collected and worked on that data for 16 more years, and fitting that amount of data, he was able to come up with the 3 important laws that are usually needed when you want the astronomy or astrophysics to understand the motion of planets. The first law says all planets move in elliptical orbits with the sun at one of the focal points. The second law, a line drawn from the sun to any planet sweeps out equal areas in equal time intervals. The third law, the square of the orbital period of any planet is proportional to the cube of the average distance from the planet to the sun. So this is how we understand the first law. The orbit is elliptical, not circular, and the sun is at one of these two foci, either this focus or that focus. Okay? The sun is at the focus, and the planet will be rotating. The planet is near the sun, the velocity, it speeds up. The velocity here will be greater than when it is far away from the sun. So the energy here would be mainly kinetic, while here it would be mainly potential energy. During the orbit, kinetic and potential energy will be exchanging, but the total energy is conserved, is constant. For the second law, the planet will sweep out equal area and equal time intervals. So here, this area is equal to this area. Okay, so here the planet will speed up because it is the same time for this part of the trajectory and this part the same time. Okay, so here to cover this area, it will speed up, it will have greater velocity compared to the part between A and B. For the third law, the square of the orbital period of any planet is proportional to the cube of the average distance from the planet to the sun. So here we know from the centripetal force, mass of the planet by the centripetal acceleration, this is Newton's second law, is equal to mv squared over r, when you substitute for centripetal acceleration. And then the force is just the gravitational force, which is g m1 m2 over r squared. So now for v is 2 pi r over the period t. We substitute here, and you take this equation and simplify, you will end up with this result. T squared, the period of one rotation, t squared is equal to this constant multiplied by r cube. Okay, ms is the mass of the sun, g is the universally gravitational constant, pi, we know it is a constant. So this constant, you may name it ks for the solar system. So you have this relationship, t squared is proportional to r cube, and the proportionality constant is ks. Okay, it's 2.09 by 10 to the minus 19 seconds square per cubic meter. This is an important law when you study astronomy and astrophysics and you want to do some calculations for the planets. So here you see various planets, some information about the masses, the mean radius, the period for one complete rotation. And you see here the ratio t squared to r cube is constant. Okay, that is the third law, Kepler's third law. Suppose an asteroid has a semi-major axis of 4 astronomical units. How long does it take the asteroid to go around the sun? From Kepler's third law, we know that t squared over r cube is constant. For a planet that has r equals 4 astronomical unit, then t is 4 to the power 3/2 from this equation. So you have 4 cubed, square root of that, 4 by 4 by 4 is 64, square root of that is 80. So the answer is 8 years. Estimate the speed of Earth relative to the sun in meter per second. speed of Earth relative to the Sun in meter per second. We know that the orbit of Earth around the Sun, it is simply the distance from Earth to Sun, which is 150 million kilometers or 93 million miles, and the period is 365 days. So you have 2 pi r divided by t to estimate the velocity. 2 pi r, this is t, the period. When we change from days to seconds, from kilometers to meters, we get this answer, 30,000 meters per second. So this would be the right answer. An object is at rest on the equator. Estimate its speed relative to the center of Earth. We know that Earth completes one rotation in 24 hours. So for this case, 2 pi r, r is the radius of Earth, which is 6.4 by 10 to the power 6 meter, or 6,400 kilometers, and the period of rotation is 24 hours. Evaluate, this is 465 meters per second, so this would be the right answer for this question. We are done with this chapter. We learned about rotational motion. We learned simply to replace v by omega, x by theta, and a by alpha, and to use the kinematic equation that we learned earlier in the course. We have a new set now of kinematic equation for rotational motion. Omega equals omega initial plus alpha t, and the angular displacement is omega initial t plus half alpha t squared, and final angular velocity squared equals initial angular velocity squared plus 2 alpha delta theta. Then we learned about tangential velocity and tangential acceleration, and also centripetal acceleration. We learned that v tangential is r omega, a tangential is r alpha, and a centripetal is v squared over r, which is the same as r omega squared. Then we learned about Newton's law for uniform circular motion. We learned that the centripetal force is given a minus sign when it is pointing toward the center, plus sign if it is a force outward, which is in that case called centrifugal rather than centripetal force. We learned about Newton's law of gravitation. Any two objects attract each other with a force that depends on the product of their masses and the inverse of the separation between the two masses. G is the universal gravitation constant. You always need it when you solve problems that depend on gravitational force. We also talked about gravitational potential energy. Then we discussed Kepler's 3 laws that we need when we study astrophysics and astronomy. The first law says that planets move in elliptical orbits where the sun is at one of the foci. And the second law speaks about the areas swept by the planet as it moves, says that the area at any given time should be the same area. And the third law says the ratio between the period squared to the radius cube is constant.